multiplying and dividing complex numbers, and DeMoivres Theorem. You should be familiar with complex numbers, including how to rationalize the denominator, and with vectors in both rectangular form and polar form. In this lesson, we will multiply and divide complex numbers in polar form, raise complex numbers to powers, and find roots of complex numbers. Throughout your mathematics education, we have built new systems of numbers to handle problems we couldn't otherwise solve. In kindergarten, you learned to count 1, 2, 3, then addition and subtraction. But subtraction gave us a problem when trying to do 2 minus 3, so we introduced a new concept, negatives. Then came multiplication and division, but we couldn't do 17 divided by 4 because there was a remainder, so we introduced a new concept, fractions, also called rational numbers. But rational numbers weren't enough to solve x squared equals 2, so we introduced real numbers. Real numbers aren't enough to solve x squared equals negative 1, so we invent an answer, called I, and arrive at the complex numbers. A complex number is written generally as a plus bi. A is called the real part, and bi is the imaginary part. To add complex numbers, add the real parts together and add the imaginary parts together. This addition is the same as vector addition. To subtract complex numbers, subtract the coordinates as you would subtract vectors. To multiply complex numbers, FOIL. Note that the last term is bdi squared and that I squared is negative 1, so this becomes the real number negative bd. In the product, the real part is AC minus BD, and the imaginary part is AD plus BC. Can we divide complex numbers? That is, can we get an answer that has a real part and an imaginary part? The answer is yes, and we will show you how to do this later in the video. Let's review the multiplication. To multiply 3 plus 8i times 6 minus 5i, FOIL, then note that I squared is negative 1, so negative 40i squared is the real number negative 40 times negative 1, which is positive 40. We mentioned earlier that complex number addition is like vector addition. It is sometimes useful to think of complex numbers as vectors, and we can write the polar form for complex numbers. It's the same as the polar form for vectors. To convert from polar form back to rectangular form, x equals length times cosine, and y equals length times sine. Here, the length is represented by r, and the direction by theta. R is found by the Pythagorean theorem, and theta via the inverse tangent. We can then factor out the r to get r times cosine theta plus I sine theta. We can abbreviate this as r cis theta. For example, the complex number with Cartesian form negative 3 minus 4i has length 5 and direction angle 233.1 degrees. The length was found by the Pythagorean theorem, and the direction angle by inverse tangent. Note that your calculator gives the answer 53.1 degrees, which needs to be moved into the third quadrant. Let's see what happens when we multiply complex numbers in polar form. First, we can multiply the lengths r sub 1 and r sub 2. Then we FOIL the terms with cosine and sine. Recall the last term has an I squared, which becomes negative 1, joining the real part. Finally, we notice that the real part, cosine cosine minus sine sine, is the formula for the cosine of angle plus angle, and similarly, the imaginary part is the formula for the sine of angle plus angle, which we can abbreviate. Let's restate what we just did. To multiply complex numbers in polar form, multiply the lengths and add the angles. Here's how division works. It is similar to the method we use to rationalize denominators. We wish to remove the imaginary part from the denominator, so we multiply by the conjugate, forming the difference of squares pattern. We FOIL the top and FOIL the bottom. Notice that in the denominator, the imaginary parts cancel and we're left with a real number. We can then split apart the fraction to see the real part is 7 over 29, and the imaginary part is negative 26 over 29 times I. Repeating this process in general, we multiply by the conjugate, FOIL, and simplify. Notice that the denominator contains cosine squared plus sine squared, which equals 1. The numerator has formulas for angle minus angle. To recap, to divide complex numbers in polar form, divide the lengths and subtract the angles. Up until now, you may think this is not very practical. After all, multiplying two complex numbers in rectangular form isn't that hard. You just have to FOIL, and it takes some work to convert to polar form and then back. Even division isn't that bad. You have to FOIL twice, but the denominator cancels nicely. The strength of the polar form method appears when dealing with exponents and roots. One way to do this problem is to expand and FOIL. That's a lot of work. Let's try polar form instead. We need to repeat the multiplication 4 times, so we raise the length to the 4th power and add the angle to itself 4 times. That is, we multiply the angle by 4. The complex number square root of 2 over 2 plus square root of 2 over 2i has length 1 by the Pythagorean theorem, and direction angle 45 degrees. To raise that to the 4th power, we raise the length to the 4th power and multiply the angle by 4. Our answer has a length of 1 and is pointing toward 180 degrees. That is pointing 1 to the left, so the real part is length times cosine, which is negative 1, and the imaginary part is length times sine, which is 0. Our answer is the real number, negative 1. We can also find roots in polar form. DeMoivres theorem says that we find roots by taking the root of the length and dividing the angle by the root. Note that since we'll be dividing by 3, to get all possible answers, we should start with our original number represented in 3 different ways by going around the circle 3 times. Negative 8i is pointing down at the angle 270 degrees, which is 630 degrees after 1 full circle, and 990 degrees after adding 2 full circles. The cube root of 8 is 2, so the length of our answers is 2. We get each angle by dividing by 3. We can then convert each answer back to rectangular form. The real part x is length times cosine, and the imaginary part y is length times sine. To recap, to multiply complex numbers in polar form, multiply the lengths and add the angles. To divide complex numbers in polar form, divide the lengths and subtract the angles. To raise a complex number to a power, raise the length to the power and multiply the angle by the power. To find the roots of a complex number, take the root of the length and divide the angle by the root. Recall that when finding the nth roots, you should get n answers by writing the original angle n times by adding full circles.